This video is all about transformers. What? No, stop it! I don't mean that sort of transformer. The national grid is a network of cables and transformers that distribute electricity around the country. Electricity is a convenient form of energy because it's fairly easily transmitted. It can be switched on and off. The problem is it can't be stored efficiently for using later. And batteries, well, they can only be used when small quantities of electrical energy are required. So we have the national grid here in the UK. Cables from power stations, wind farms, etc. are connected to this nationwide network, so electricity can be generated in different places away from towns and cities, and the demand met 24/7 in those towns and cities. The engineers at the central control of the national grid continually assess demand, direct the flow, and reroute electrical energy when needed. In this video we're revising transformers, so we need to see where they fit into the national grid. No, I still don't mean you. It's quite enough of that, I think, don't you? We start at the power station, where an AC, an alternating current, is generated. The voltage of this alternating current is then changed in a transformer. It's stepped up to increase the voltage to 400 kilovolts. And this is done to transmit electrical energy more efficiently. Remember, efficiency is a measure of how much useful energy you get out from the total energy you've input. When electric current flows, wires heat up. And sometimes that's great, but it's really not useful when you're trying to get the electrical energy across the country. So the voltage is increased in the step-up transformer because it allows the current to be made much lower for the same power. Because power is equal to current times voltage, as the power stays the same in the transformer, as the voltage increases, the current decreases. And so does the heating effect in the wires. The disadvantage of transmission lines being at 400 kilovolts is it's a seriously high voltage, so it's dangerous. Before the electricity can enter your home, it's stepped back down again to 230 volts. And this is done using the other type of transformer, a step-down transformer. So if you had a calculation question, here's an example. You can see I've highlighted the relevant bits of the question. I've worked out which bit is the voltage in the primary, the voltage in the secondary, the current in the primary. And I've worked out the power in the primary coil because I know both the current and the voltage there. Remembering that the power will stay the same, I then got the power to use along with the voltage in the secondary to calculate the current in the secondary coil. So, transformers are part of the national grid. They step up the voltage to transmit the electricity more efficiently and then step the voltage down to use in your homes. But before we can finish by explaining how a transformer works, how it can change the voltage to a higher or lower value, we need to review two things: electromagnetism and induced current. It was Hans Christian Ørsted who proved that the current-carrying wire had a magnetic field around it, and this led to our use of electromagnets, which we can make into very strong magnets that have that advantage of being turned on and off. To increase the strength of an electromagnet, you coil the wire using lots of turns in your solenoid, and you put a large current through it. Stick a piece of iron through the middle, and when the current flows one way, you have a north pole at one end of the iron and a south pole at the other. And then if you reverse the polarity of the current, you change the direction of the current, You reverse the direction of the magnetic field. It was Michael Faraday who discovered that if a wire moves relative to a magnetic field, so it cuts the field lines, the electrons in the wire start flowing. A current is induced. This current is stronger if you use more wire, so let's coil it up into a solenoid again. And if you push the magnet through the solenoid, a current is induced. To induce a bigger current in the same solenoid, you use a stronger magnet or move it faster. Or you could always use a solenoid with even more coils to get a bigger induced current. When you push the north pole in first, you get a current that flows in one direction. And if you go south end first, the current will flow the other way. So let's pull all those ideas together and explain how a transformer works. An alternating current flows back and forth in the primary coil. This creates a changing magnetic field in the iron core. In the secondary coil, there's now a changing magnetic field, so it's moving relative to the coil, and a current is induced in the coil. First one way and then the other, so it's an alternating current. Transformers only work with an AC source, not with a DC source. Because with DC, when you turn it on, the current will flow into the primary coil, but in one direction. So you get a magnetic field in the iron core and an induced current in the secondary coil, but then nothing. It would be like you're holding the magnet stationary inside the secondary coil, so no current would be induced. If you turned it back off, you'd get a spike of induced current again. It would flow in the opposite direction, because it'd be like the magnets being pulled out of the secondary coil. Transformers do not work on DC. So we already looked at some maths. Remember, the power was constant across the transformer, so the voltage times the current across the primary was equal to the voltage times the current across the secondary coil. We could use the power equation to work out the voltage or the current in any part of the transformer. But that's not the only thing you can calculate. It's the ratio of the turns between the primary coil and the secondary coil that decide how much voltage will be stepped up or stepped down. A step-up transformer has more turns on the secondary coil, so a small voltage in produces a large voltage out. In a step-down transformer, there are more turns on the primary coil, so the high voltage in becomes a smaller voltage out. The ratio of turns allows us to calculate the expected voltage because it will be in the same ratio. So let's have a look at an example. Here I've highlighted the relevant bits of the question again to identify the number of turns on the primary, the number of turns on the secondary, the primary voltage, because it's the secondary voltage we're trying to find out. I've used the equation, I've substituted the numbers in, I've calculated when I can, and I've used the triangle to rearrange the equation at the end to work out the voltage. Now, there are more turns on the primary coil here, so I would be expecting this to be a step-down transformer, and therefore when I see my answer of 0.5 volts, and that's less than the 12 volts, pretty sure I got it right. So there you go, we revised transformers, and you know that.
Regular review gets a better grade for you.
Don't forget to
Like,
so that I can keep making the videos.
comment,
Especially to request other revision topics.
subscribe.
So you can get notifications of when my next video gets uploaded.